Hi, everybody. Welcome back. This is section 2.7 in Calculus 3. And so this is our last section in this first chapter we are studying together. The topic of this section is the different coordinate systems. So you are familiar with what is known as the rectangular or Cartesian coordinate system. It's X and Y or X, Y, and Z. But you have also studied the polar coordinates in two-dimensional plane. It turns out in 3 dimensions, we have 2 additional coordinate systems, and that's what we'll study. All right, so stay on and we'll just get started now. All right, so the first thing you should do is to print out the handout. The handout should be on your page for section 2.7, and it's called Cylindrical and Spherical Coordinates. So let me go ahead and write down the section number, section 2.7. Incidentally, we will not be using these ideas right away. When we go into chapter 3, we will not use this. And in fact, we will not be using these coordinate systems until our integration, which is the last half of this course. But it is good to know these things before we get more seriously into our calculus portion of Calculus 3. I know it sounds strange to say the calculus portion of Calculus 3 as a course, but this first chapter really is without any calculus proper, so to speak. All right, so what are the cylindrical and spherical coordinate systems? Here's a basic idea, right? As I said before, right? To express a point on the plane, you first learned rectangular or Cartesian coordinate system. All right, so the idea is you have this vertical and horizontal axes, and these are, of course, the horizontal one is called the x-axis. Let's use the black here. And then the vertical one is called the y. You can pick any point P, and you can describe the point P using the x and y coordinates, right? So from the origin, how far right do you go? That's your x, and how far up you go, and that's your y coordinates. Incidentally, the person who came up with this idea first was the French philosopher René Descartes. And so his name, just like most other French names, has a bunch of extra letters in there, right? But you do not pronounce his name Descartes. His name is Descartes. And somehow this DE disappeared, or DES disappeared when we talk about the coordinate system. And so this is known as the Cartesian coordinate system, not Descartes coordinate system, right? Because it's based on rectangular coordinates, this is often called the rectangular coordinate system. So if I talk about the rectangular coordinate system, remember it's the one with x and y. But that's not the only one you learn. All right, so later, probably like in your trigonometry class or pre-calculus class, or maybe in calculus or pre-calculus or trigonometry or algebra 2, or in your kindergarten algebra class, you learned about this other one, right? So you can describe this point also using not x and y, but here's a point P, how far it is from the origin. Let's use a different color here. And how, oh, what is that? I just missed it. That was a bad swing. What is going on here? Okay, there's a conspiracy going on. Yeah, something's wrong with my pen. I cannot even draw a pen. This is terrible. Okay, so I give up. Maybe I should not be doing this. Okay, so instead of that, I'm going to draw this line here like this. Okay, so you can find P and describe it in terms of how far it is from the origin and what the angle is as you go counterclockwise from the positive x-axis, right? And so this will give you r theta as the coordinates. And this is called the polar coordinates and the polar coordinate system. So the point r theta also represents the point P. All right, why do we need 2 systems anyway? Well, as you learned in maybe when you studied polar functions, you know, theta or R is a function of theta. Many times if the figure involves a circular part or part of a circle, like semicircle or something, it's much easier to do things in polar coordinates. And so that's why we have these two coordinate systems, just like, two languages. One is more easily understood in certain countries than the other one. So now we go into three-dimensional space. Ooh, then what? You can still use the rectangular coordinate system, Cartesian coordinate system, except with X, Y, and Z now, okay? But then it turns out we can create, and some people have even created more than these two, but there are two other coordinate systems that are quite useful in Calculus 3. And one is called cylindrical, and the other is spherical. Okay, if you look at the cylindrical coordinate systems, you don't see any other additional letters. You have R, theta, and Z. Okay, and simply put, I mean, this is really R theta, the polar, plus Z. Right, so you just add the vertical component Z to the polar coordinate. That's cylindrical. Very easy to understand. The trouble is with the last one, spherical. Okay, look at that. What do you see here? You see a P? No, it's not even a P, right? So what you see is this Greek letter, which looks like a P, but just like this in Greek, this is actually our corresponding to our letter R. This is the Greek letter rho, okay? And then you have theta, which is the same theta, which turns out to be the same theta as in the cylindrical coordinate system. And then the last one, this looks like that, the empty set. I usually write the cursive version of this, which is this, and it's called phi or phi. I often call this phi, and this is theta, and this is rho. So rho, theta, phi, and this represents a point in the spherical coordinate system. And people said, oh, it's all Greek to me. Yeah, it is. I mean, every letter is from the Greek alphabet. Okay, but it's not as hard as Greek. Well, really, right? So hopefully we will be able to understand this and make full use of this. All right, so what can I do? So maybe I should write down these letters here. This is how we write that letter rho, and this is theta. And this is phi or phi, and I often just call it phi. Right? The capital letters are different, but they're similar. I mean, this sounds like a like a fraternity house or something. Okay, so what do you know about X, Y, and Z in the cylindrical coordinate system? Well, in the cylindrical coordinate system, and this is a picture of it. Right? So here's the origin, okay, and this is the X-axis, Y-axis, Z-axis as usual. If you want to try to represent this point here, basically you project it down to the XY plane and try to write the coordinates of this point using the polar coordinate system. So what is this length X, right? So you know how far this X is. This is your Y, this is your R, right? And this is the angle theta. So if you look at this from the top, I mean, this is exactly what you're looking at. Here's X, and here's your Y, right? And so X, as you know, is R times cosine of theta. Because if you say R, that's the hypotenuse, times the cosine of theta, that's going to give you the X coordinate easily. Y is R times sine of theta. No problem here. You knew that too, right? This is the opposite of theta, so it's R times sine of theta. Z, well, it's actually just Z because we use that same thing in polar or a cylindrical coordinate system. So the Z in the cylindrical coordinates and Z in the rectangular coordinates are exactly the same. Easy, right? Now, if you want to go the opposite, see here, I have tried to find the rectangular coordinates, X, Y, and Z in terms of polar or cylindrical coordinate system. If you want to go the other way, using X, Y, Z to represent R, theta, then what do? Well, R, as you know, is simply the square root of X squared plus Y squared. Theta, ooh, that's a little trouble, isn't it? Okay, what is theta? How do you find this angle? Well, the problem is this theta is not unique. I mean, if this theta, for instance, is 40 degrees, you can also call that 400 degrees, right? Plus or minus 360 degrees, and it's going to give you the same thing. So there is no clear formula for theta. All you can say is the tangent of theta is this divided by that. That's tangent of theta is y over x. I don't want to even write the theta is the inverse tangent of y over x, because the inverse tangent only gives you an angle between negative pi over 2 and positive pi over 2, right? So and this is how I'm going to just say that. And this is not even, good enough, because what happens if x is equal to 0? Then the theta, of course, is going to be either a pi over 2 or negative pi over 2. But remember, I mean, if x is 0, this doesn't even make sense, right? So just keep that in mind. Theta is not unique, and not unique. And even this expression is not quite sufficient, because sometimes x is equal to 0. All right? Yeah, good. All right, so that's your cylindrical coordinate system. Not bad, right? Right, so let's go to spherical. Ooh, look at all that. And then we'll do some exercises. All right, so here's a picture. Now, this is by far, and let me just tell you this, I've been teaching calculus 3 for many years now. This is the picture for you to remember when you are to think about the spherical coordinate system, okay? If you understand this picture, if you can draw this picture, if you put this picture in your brain, okay, and don't let it leave, then you can figure out all of these things. And so I hope this will make sense, all right? So here's a point P, X, Y, Z. Right, now I wanna describe this in terms of rho, theta, and phi. All right, so bear with me here. First of all, what is rho? Okay, rho is the distance between the origin and this point. You see that? This is rho, okay? So that's how far it is from the origin. If rho is constant, you have sphere, and that's why it's called a spherical coordinate system. So if rho is a constant, you get some sort of a sphere centered at the origin. Okay, so that's what rho is. Theta is the same theta that you saw before. This is this angle that the projection of this point P onto the XY plane makes with the positive x-axis oriented in a counterclockwise. So starting at the positive x-axis, we measure how far, what degree, or how many radians you have to go until you get to the vertical plane through origin on which P lies. Or in other words, how far is this point, or the projection of the point on the XY plane with respect to the positive x-axis. Okay, that's theta. Same theta as in the cylindrical and the polar coordinate system. All right, and then how about phi? This is the trickiest coordinate. Phi is the angle that this point, the point, well, you have a point OP, right? I mean, this is a vector. Okay, so phi is the angle that this vector OP makes with the positive z-axis. So here's the picture of this. This is your phi. You get that? All right, that's your phi. And by the way, the z-axis is of course vertical, right? When you do this projection from P onto the XY plane, that's also perpendicular to the XY plane, right? So if you call this phi, this is the angle phi, there's another angle that is congruent to phi, same angle measure as phi. You know where that is? Because of the property that two alternate interior angles are congruent. You see that this is parallel to this line here. So this is also phi. So the angle phi is represented by two of these angles, two congruent angles here. And I want you to notice this very important thing here. Let's go ahead and try to do this. The line here, that's OP, right? From P to the projection onto the XY plane. And then from O to this projection here. Okay, that's a triangle, right? You see what kind of triangle it is? It is the right triangle, because this is a right angle. I know it sort of doesn't look like it, but it is, right? I mean, this is vertical, and so that is a right triangle. The hypotenuse is rho. This is really key for you to understand this. Now, we used to call this length R, and so R, R can tell you what this X is and what the Y is, right? So this is also an important part of this. And this vertical segment, the length of that is called Z. This picture tells you everything you need to know about the relationship between x, y, z, theta, rho, and phi, okay, and r. So what is rho? Okay, so rho, I think you can see rho is the square root of x square plus y square plus z square, if you are given the rectangular coordinates of a point, okay? And that's just the distance formula. Now you could also write this, because x squared plus y squared is rho square, r square. This is the same thing, okay? You see that? Yeah, this is r square plus z square is equal to rho square. That is the Pythagorean theorem. Pythagorean was also Greek, okay? R, how do you find this R? Well, let's think about this triangle, the green triangle, right? So the green triangle, here, let's go ahead and draw the green triangle. Can I draw a green triangle, please? Yeah. The green triangle looks like this. Oops. Yeah, that's not it. It's supposed to be a right angle. Something is not right with my pen. Okay, so that is, it's okay here. This is your zero, O, and this is your P, and this is your, let's call this point Q. Okay, this is the right angle here. This is rho, okay? This is Z, and you see OQ, that's your length R, right? So your R happens to be, and by the way, the angle here is theta. So the R happens to be, and figure this out. Maybe you can just try to tell me what this is. What is R? How do you write the expression for R in this triangle, in this right triangle? It's the opposite of phi, right? So this is going to be rho sine of phi. Get that? Rho sine of phi, because R over rho is the sine of phi. How about Z? Z is the adjacent side to the angle phi, and so the answer to this is rho times cosine of phi. Like I said, if you know this picture, you can reconstruct all of these. Now, x happens to be r times cosine of theta. Remember that? That's from the previous one, from the polar coordinates or cylindrical coordinate. We know how to write r now. R is rho sine phi. So x, based on the spherical coordinates, x can be written as rho sine phi cosine theta. Rho sine phi will give you this length, and then multiply that by cosine of theta will give you this distance. Y was rho sine theta, right? And R is rho sine phi. So R times sine theta is called rho sine phi sine theta. All Greek to me? No, that's not bad, okay? And so these are the ways to convert from spherical coordinates to rectangular coordinate system. Now theta, again, this is still the same thing. There's no nice way of writing theta. The only way is tangent of theta is x divided by y, y divided by x, as long as x is not 0. Now how about phi? Okay, phi is also a little tricky to write. You could write phi is the inverse tangent. What's a tangent of phi? The tangent of phi is r, the opposite over the adjacent, r over z. So you can write that, and make sure your phi is always between 0 and pi. Do you see why that is? See, right now, this phi looks like about 45 degrees. That's pi over 4, right? If phi is pi over 2, it's all the way down to the xy plane. If phi is pi over pi, then it'll go from here all the way down to the the negative x-axis, negative z-axis. And so phi is no bigger than pi under any circumstances. All right, now on the back, you have these things. Okay, you may want to just pause this, and I'm going to give you a break, and then when we come back to the second part of this video, then I will have these filled out, and you can use the formulas, but I do want you to think about and sketch all these, because that would be a much better way to understand and really have a good grasp of convergence, the understanding the relationship between rectangular and cylindrical coordinates, or rectangular and spherical coordinate systems. Okay, so see if you can describe these points in the other two coordinates. All right, we'll be back.